video, we're going to start Chapter 11. And Chapter 11 is on alkynes. Remember, alkynes are our functional group where we have at least one carbon-carbon double bond. We did name alkynes in the last chapter with alkenes, so I'll talk real briefly about naming, just a quick reminder, but for the most part, we're going to jump right into reactions of alkynes. So just do remember, our alkynes have a triple bond between them, right? Remember, whenever we have a triple bond, we actually have two pi bonds holding them together, right? Each of these carbons is sp hybridized, right? If it's sp hybridized, it has two sp orbitals and then two unhybridized p orbitals. So if I was to draw my picture, my bonding picture for this, right? My sp orbitals, one overlapping with the s orbital of hydrogen, my other sp orbitals overlapping with the s orbital of hydrogen, and then I'm just going to pick a different color here. I have an unhybridized p orbital, and then those are overlapping, right? It's one pi bond there, right? They're overlapping for the pi bond, but it overlaps in two spots. So even though I'm connecting it in two spots, that's one pi bond. And then in the other plane, I have another p orbital, and then those are overlapping to form my other pi bond. Remember, these are linear. So when we're naming them, I don't have to worry about stereochemistry, right? I can't have groups above or below, right, on opposite or the same sides of my pi bond because they're in line with that pi bond, right? Again, if we look at this one, those are linear. So it's linear. I don't have to worry about stereochemistry about that triple bond. Now, just because I have a triple bond on a molecule, be careful for this, right? I could also have a double bond. So if I do something like this, right, where I don't have to worry about stereochemistry here, I do have to worry about stereochemistry here. So don't just say, okay, I have a triple bond, I don't have to worry about it. You could have other things further on down the line on that molecule where you do need to pay attention, but there isn't stereochemistry about the triple bond. So no EZ, no cis trans, right? It's linear. Just speaking of naming, remember our ending does end, in YNE. And again, we did cover that with alkynes, so I'm not going to go into naming other than to just remind us it ends in "-ine", and there's going to be no stereochemistry about the triple bond. Jumping right into reactions then, I do want to do one preparation first. Remember, preparation are where we're preparing that molecule. So an alkyne is going to be my product. So we're just going to have one of these, and I'm going to start with a molecule where I have a halogen on adjacent carbons. And then we're going to have strong base. I do need two equivalents. Sometimes we'll actually put a 2 in front of it. It could be written that way. I could do strong base with two equivalents written after it. And I would actually give you a strong base. I wouldn't just write SB. I would give you like sodium hydroxide. We could also do the strong base, and I could write excess after it. All of those things are going to essentially mean the same thing. So for each one, right, dihalide, I need two equivalents of strong base. I need to have more strong base, I need to have excess than I do my dihalide. So again, all of those things meaning the same thing. And then the strong base is typically going to be either a hydroxide ion, I could use hydride again, or NH2, any of our typical strong bases. And we're going to do an elimination. So it's essentially just going to be a double elimination reaction. I'm going to end up with that alkyne and then two HX molecules. So it's going to be two eliminations. I am going to go through a vinyl halide intermediate. We'll do the mechanism and I'll show you that. Remember, a vinyl halide is where I have the halogen attached directly to that sp2 hybridized carbon. So I am going to go through a vinyl halide intermediate. My mechanism. So I do have, let's actually use a real halogen. So we'll use chlorine. There is a hydrogen there. Here I have a hydrogen and a chlorine. And my strong base, we'll use hydroxide ions. And I'm essentially just going to do two E2 reactions. So I am going to take that hydrogen the same time that those electrons go down at the same time that the leaving group leaves. It does follow all of the normal E2 things, so that hydrogen that I take should be anti, right, to that chlorine. That's supposed to be a wedge there, meaning that this one is going to be in this direction and this one is going to go that way. I'm not going to draw the transition state. You did need to draw the transition states, that's hard to say, back in chapter 8, but I'm assuming that you know how to draw them now. So I have a chlorine here still, and then I have a double bond. So this is that vinyl halide intermediate. I'm then just essentially going to repeat that. Let me get this out of the way. Those two carbons there's still that hydrogen here. Those carbons now in the double bond are now sp2 hybridized. They were sp3. They're now sp2, so they are planar. So I'm not going to wedge and dash those anymore. I'm going to leave them in the plane of my iPad here. And then another equivalent of base. I'm going to take a proton, those electrons are going to go down to form that triple bond, and then I'm going to lose my next leaving group. And then be careful when you draw this, it's now linear, so we want to make sure we draw it linear, right? So I actually went from sp3 hybridized carbons to sp2 hybridized carbons to sp hybridized carbons. So from tetrahedral to trigonoplanar to linear, right? So my geometry changed also as we went through that. Next, we'll go through some reactions. And the first ones we're going to do are going to be electrophilic addition reactions. So very similar to what we did with alkenes, in chapter 10. It's just that instead of having 2 pi electrons to react, I'm going to have 4. So I am going to add HX. It's just that I'm going to do it twice instead of once. So addition reactions first. And our first addition reaction is going to be a hydrohalogenation. So we're adding HX. So we're taking our alkyne, and I'm going to make this unsymmetrical. So I'm going to make it a terminal alkyne, meaning that my triple bond is on the end. And then I'm going to add HX. And then we do need 2 equivalents or excess. It could be written any of those ways. So excess, right? I could write 2 equivalents. I could put a 2 in front of it. Any of that notation means the same thing, or essentially the same thing. And my halogen can be chlorine, bromine, or iodine, same options that we had with alkenes. And then I am going to follow Markovnikov's rule, just like we followed with alkenes, right? When I did HX across the double bond, I went through the more stable carbocation intermediate, so my halogen ended up on the more substituted carbon. My halogen is going to end up on the more substituted carbon here, which is why I wanted to make it unsymmetrical. And that's going to happen with both steps, so we're going to end up with the 2 halogens on the same carbon when we're done. we are going to go through the mechanism. I'm going to do it rather quickly because, again, we have seen this mechanism before. We're just doing it 2 times. We should add Markovnikov product, which for some reason I can't spell today. So we want to go through the more stable carbocation intermediate. We end up with the halogens on the more substituted carbon. So more stable carbocation forms, halogens on the more substituted carbon. So my mechanism, let's use HI. I don't use iodide a whole lot. So same mechanism as before, right? That hydrogen is partial positive because it's bonded to the more polarizable iodine molecule. So my pi electrons, which are nucleophilic, right, my electron source, are going to grab onto that partial positively charged hydrogen. I then need to break the bond between hydrogen and iodine, and I do that by putting those electrons onto iodine as a lone pair. I want to end up with that positive charge on the more stable, or I want that carbocation to be more stable, so I want the positive charge on the more substituted carbon. So I end up with this intermediate. I have iodide floating around. So it's going to add, that's a crazy looking arrow. Let's make it a little prettier. That's not any better. My positive charge is in the way. Let's move it. It goes there. I just can't make my arrow look good, which of course I'm pretty weird about those things. So it's going to grab onto that carbon. And we do end up going through that vinyl halide intermediate again. So vinyl halide intermediate. Right? Here we want our positive on the more substituted carbon. And then we just do it again. So I'm going to add another equivalent of HI. I still have pi electrons. I still have a partial positive hydrogen. So we're going to grab onto that hydrogen and then break the bond that the hydrogen originally had, putting those electrons onto iodide. Again, I want the more stable carbocation intermediate. So I'm going to put that positive charge on the more substituted carbon. I have another iodide floating around. It's going to attack that electron deficient non-octet carbon. And then we end up with our product. This intermediate is planar, right? This one here, so that iodine can add from either side, from the front or the back. I'm not showing that because I have 2 iodides on the same molecule. So whether the second one comes from the back and the first one's from the front or vice versa, it's the same molecule, right? It's not chiral. Even if I made these carbons, right now I have 1 carbon-based group each on that carbon, the carbon in the center, right? This carbon, it's kind of confusing when I say it like that. This carbon here, right, has 2 1 carbon groups attached to it. So even if that was unsymmetrical, it's still not going to be a chiral center because I'm going to have 2 of the same halogen attached to it. So though all of the normal rules apply when I go through a planar intermediate, in the end we can't tell. So I'm not going to worry about showing stereochemistry there though. Regiochemistry does matter, right? It is regiospecific. It does follow Markovnikov's rule. So it is regiospecific. It's not stereospecific, right? It's a planar intermediate, so I can get both products. I don't even really have to show that though, because in the end I have a non-chiral carbon. It does go through that vinyl halide intermediate. So I don't go directly from an alkyne to my alkane, right? I am going through an alkene intermediate. And that's going to be true for all of the addition ones that we do. My second one is going to be a halogenation. So this is where we're adding, I'm going to make it unsymmetrical again. I'm adding X2, where my halogen is either chlorine or bromine. And then again, I need two equivalents. It needs to be XS. I can put a 2 in front of it, but we're going to do the reaction twice. So I do need more than one molecule of that. And then I'm going to end up with 4 halogens on there. There is a hydrogen on that end carbon also. The mechanism is going to look very similar to what we did in the last chapter, but again, we're just going to do it twice. It is going to go through that bromonium or chlormonium intermediate. So we'll use bromine. Right, I do have lone pairs on both of those bromines. I do have an induced dipole. So these electrons are going to grab onto that bromine. A lone pair is going to come back and grab onto that carbon, and then we're going to break this bond. Positive charge. And then my second bromine, it is going to attack the more substituted carbon. This is regiospecific. It's just in the end, again, we don't really notice. But when you do the mechanism, I will see that you're attacking the correct carbon versus attacking this carbon. If you were doing that, then you're not following Markovnikov. So we're going to grab onto that. We're going to break this bond. Wrong color. And then I do have that double bond there still. I'm going to have this bromine coming up. I'm going to have this bromine going down. Remember, this is stereospecific because that bromonium ion is blocking one side. My bromide ion, right, needs to attack from the opposite side. So I do have this. It is a vinyl halide. I have 2 halogens on there, but I do go through that intermediate. And then we do it again. So pi electrons grab the bromine, lone pair grabs onto that carbon, and then those electrons go onto bromine. Drawing that intermediate, I now have a single bond there. I do have a bridged bromonium ion. I have a bromine and a hydrogen on this side, and then a bromine and a methyl group on the side, positive charge. Bromine floating around. So it's now going to attack again the more substituted side. So I'm going to have it grab onto this carbon, and then we're going to break that bond. And we end up, I guess the way, I'll leave that little methyl group up, I'll draw it this way. So I have 2 bromines here, and then I have the 2 bromines here. And then from a stereochemistry standpoint, right, the original 2 are anti to each other, and then the second 2 are anti to each other. But if we were to draw all of that, wedges and dashes, which we can do, you can't really differentiate because we have 2 halogens on each one. Again, do pay attention when you're doing the mechanism though, because I will be able to see which, from a regiospecific standpoint, which carbons you're attacking. Make sure that this intermediate is anti. And actually, we should say, assuming that the halogens are the highest priority group, we should actually say Z, but we want the halogens anti to each other. The molecule itself is E in this case. Sometimes we do show the solvent with this reaction. I'm just going to go back up. And this is the same with alkenes. So for the halogenation reaction, sometimes you'll actually be shown the solvent. That's fairly common. So if you see dichloromethane, so CH2Cl2 also with X2, don't be thrown by that. It's just showing the solvent. And that is pretty typical. So also with alkynes. So if we had an alkyne, and I gave us Cl2 and then dichloromethane, right? We end up with this as our product. And then an alkene, this time we have to have excess or two equivalents, and then again, carbon tetrachloride. It would go through that trans dihalide intermediate, but in the end, I end up with the 4 chlorines on there. So the only difference from what we've done before is I just added the solvent in here, just as an example. So it is pretty typical to see that included. So again, it just, if you're looking at other sources, and sometimes I'll include it, I don't want it to throw you off. I don't want you to think that it's something different. So for both alkynes and alkenes, when we're doing halogenation reactions, dichloromethane is our usual solvent. We are going to do hydration reactions also. So remember, with hydration, we're adding water. And then just kind of reviewing our alkenes. So a little side note, remember we had 3 different ways to do it, right? Our first one was acid catalyzed. So we used sulfuric acid and water. We needed the mechanism for that, and I used hydronium ions typically as part of the mechanism. Our second way was oxymercuration, so we used mercury acetate, and then in a second step, sodium borohydride. Often we would have solvent and things thrown in there also. And then our third one was our hydroboration, so BH3, usually tetrahydrofuran, THF. And then a second step, hydrogen peroxide and hydroxide ions, right? Those were our 3 methods for alkenes. And I want to have them there because when we look at our alkynes, we're going to have 2 methods, and it can be kind of confusing because we're going to essentially take the material from our number 1 and number 2 for alkenes and kind of combine them. So instead of using sulfuric acid and water in one reaction and then mercury acetate in another reaction, we're actually going to use sulfuric acid and mercury sulfate. It's not really a combination of the 2. It's just that I'm taking reagents from both. And oftentimes when you have 2 chapters where the reactions are that similar, it's really easy to get things mixed up. So I'm only mentioning it so that way you want to try to make a note that it's different. It's not just taking the reactions from the alkenes and doing it twice like we did with the hydrohalogenation and the halogenation. There is some differences on this one. So I am going to have the 2 methods again. They're just going to be different than they were with alkenes. So my first one, I'm going to use mercury sulfate. Acetate has a -1 charge. It is mercury 2 ions, so I needed 2 acetate for every 1 mercury. Sulfate, however, has a -2 charge, so it's a 1-to-1 ratio. Often we'll need water, and then we are going to use sulfuric acid. So it's actually acid catalyzed with the mercury. So just be really careful to keep those straight in your head. I am going to follow Markovnikov's rule, and we're going to go through an intermediate, actually an enol intermediate. Remember, with hydration, the net effect is to add water. So I'm going to add hydrogen to one side, OH to the other. You're not responsible for the mechanism for this one. That's because that's not the mechanism, right? But that's kind of our net effect. And we're going to end up, let's actually do that. I am going to follow Markovnikov's rule. So I'm going to end up with the hydroxyl group on the more substituted carbon. And then this is going to be an enol intermediate. En because I have an alkene, and then ol because I have an alcohol group on the same carbon. So because this carbon right here has both the double bond, an alkene, and an alcohol group, we call this an enol intermediate. And then that's actually going to further react to give us our final product. And our final product is actually going to be a ketone. Going from the enol to the ketone is a mechanism that you're likely to learn in 236. It's a tautomerization reaction, which is kind of a fun word to say. And it is a rearrangement reaction. Remember back in chapter 6, we talked about types of mechanisms. We had pericyclic, types of reactions, not types of mechanisms. We had addition, elimination, substitution, and then rearrangement. So this is a rearrangement reaction. My enol and my ketone are structural isomers of each other. Generally, that process is acid catalyzed. It could also be base catalyzed. In 236, you're likely to look at both of them. Here, it's acid catalyzed because we're adding sulfuric acid. So it does follow Markovnikov's rule. Let's add that here. So we get the Markovnikov product. So what that means for us, when I get to that Enol Intermediate, I want the hydroxyl group on the more substituted carbon. And then when I tautomerize to get my final ketone product, the carbon that had the hydroxyl group on it is going to be the carbon that has the carbonyl. So my carbon that was bonded to the hydroxyl is my carbonyl carbon. So we want the hydroxyl group on the more substituted carbon. If I had a non-terminal alkyne, right here my alkyne is on the end, so it's terminal. If it was non-terminal, and I still want to make it unsymmetrical, which is why I'm doing this. So just be careful not to lose carbons. I have 1, 2, 3, 4, 5 carbons. So for this one, when it reacts, both carbon 2 and 3 in this reaction are equally substituted, right? They both have one R group on it. So if I'm reacting this using mercury sulfate, water, and sulfuric acid, H2SO4, I'm actually going to get two different products. And I usually like to draw the Enol Intermediate. It's easier for me to visualize the product if I do this. So my double bond is between carbon 2 and 3, and then I can have one intermediate where my hydroxyl group is on carbon 2, and then I can have another intermediate where that hydroxyl group is on carbon 3. Right? Carbon 3 has one carbon-based group bonded to it. Carbon 2 also has one carbon-based group bonded to it. So they're equally substituted. When these tautomerize then to give me my product, I'm actually going to end up with two different ketones. One where the carbonyl is carbon 2, and another one where my carbonyl carbon is carbon 3. And I actually would be looking for both of those products. So if it's an internal alkyne that's unsymmetrical, we're going to get two different products. If it was symmetrical, if I did this, right, 1, 2, use a different color so it's easier to see, and maybe make it big enough so you can see 1, 2, 3, 4, right? If I number from that direction, or if I number from this direction, 1, 2, 3, 4, it's the same thing. So whether I put my hydroxyl group here or I put my hydroxyl group here, it's not any different. Those are the same. So in both cases, I'm going to end up with a ketone on carbon 2, right? For this one, 1, 2. For this one, 1, 2. And I do want you to know that those are the same thing. Like if you give me both of those answers and tell me that it's two different products, I am going to take off for that. So do be careful. If it's internal, right, meaning my alkyne is not on the end, it's somewhere in the middle, and it's symmetrical, I'm going to get only one product. If it's unsymmetrical, I'm going to get more than one product. So do be careful for that. So my hydroxyl group is going to go on the more substituted carbon because it's going to follow Markovnikov's rule. be careful for that. In this case, these two carbons were equally substituted, so we end up with two different products. This one, I had one carbon base group on this carbon. I had no carbon base groups on that carbon, so I only get the one product. So make sure you pay attention to regiochemistry when you're doing these. My second method, and I'm going to use a terminal one again, so that way it's unsymmetrical. And we're going to use BH3, THF, and then hydrogen peroxide and hydroxide ions. And then this one's going to go through an Enol Intermediate also, but just like in alkynes, this gives us our non-Markovnikov product. So instead of putting my hydroxyl group on the more substituted carbon, like we did with our first option, I'm going to put it on the less substituted carbon. So I am going to go through an Enol Intermediate. So I have a double bond there, but I'm going to put my hydroxyl group on the less substituted carbon. So Enol Intermediate. Non-Markovnikov. So my hydroxyl group on the less substituted. Carbon. So then this is also going to tautomerize, right? I'm going to undergo a rearrangement reaction to get my final product. The carbon that has the hydroxyl group does become my carbonyl carbon. It's just that in this case, it's on the end. So I end up with an aldehyde functional group, right? Up here I didn't write it down, but we end up with a ketone. So ketone functional group. This one we end up with an aldehyde functional group. And that's if it's a terminal alkyne, right? If the alkyne is internal, right, if it's not on the end, then they're equally substituted, and I'm actually gonna get the same products that I would if I used the mercury 2 sulfate and sulfuric acid, right? If we were to go, I'm gonna just do the same one we did here. CHF, hydrogen peroxide, hydroxide ions. Let's number them again so I can refer to these carbons. I am going to go through my Enol Intermediate. I'm going to put my hydroxyl group on the less substituted carbon. Both of those carbons have one carbon base group, so they're equally substituted. So I'm going to get both of these Enol Intermediates. And then when it tautomerizes to give me my final product, I actually get ketones again. If it was a symmetrical alkyne, right, symmetrical and terminal, we should say, I'm actually going to get just the one product again, being the same products that I get with the mercury 2 sulfate and sulfuric acid. Right? I have 4 carbons. When I draw my Enol Intermediate, this carbon is as substituted, right? It's equally substituted to this carbon. Those two are the same, so I'm just going to draw one of them. And then when it tautomerizes, I get one ketone, right? Either that one or this one. It doesn't matter which one you draw, just don't draw both because they're the same thing. So if it's a terminal alkyne, I'm going to get an aldehyde, or an aldehyde. If it's internal, I'm going to get a ketone again. So do be careful for that. Ketone, if internal, meaning it's in the middle somewhere, just not on the end. Okay. So if I gave you just another example for us. And then I always have to number my carbons because I lose them. 1, 2, 3, 4, 5, 6, 7, 8. And I don't put anything on the line, but then I give you these products. So numbering them. Don't lose carbons. I'm really bad sometimes for losing carbons, which is why I like to number them. Even if you don't literally write the numbers down, you know, kind of do it in your head. So if I give you this product, let me finish the product, and then we also get this one, and you have to decide what goes on the line, you can pick any, right? Or I shouldn't say any, but either, right? If I was to choose this set of reagents, those are the products I get. And if I was to choose those reagents, I get the same set of products because my alkyne is internal, it's in the middle. So I'm gonna get ketones either way. If it was on the end, now there's gonna be a difference. I'm gonna get aldehydes versus ketones. The next couple reactions of alkynes that I want to talk about are actually going to be substitution reactions instead of addition reactions. Before we do those, we do need to prepare our alkyne. So essentially, alkynes are weakly acidic. Alkanes and alkenes are not. And we talked about this early on in the semester when we were talking about acidity trends, right? We said that generally the more stable the conjugate base, the more likely it is to form, so the more likely that acid is to lose its proton, right? So stronger acids tend to have more stable conjugate bases. And then we had a list of reasons as to why our conjugate base could be more stable, right? We had resonance effects, element effects, inductive effects, and then we also had hybridization effects. So remember that if I look at this, right, I'm going to show the hydrogen. Usually I don't, but we'll show the hydrogen. Remember, this carbon is sp hybridized. If I was looking at an alkene, right, I have 2 hydrogens on here, but that carbon is sp2 hybridized. And if I was looking at an alkane, I guess I have 3 hydrogens. That carbon is sp3 hybridized. So once I lose that proton, if I add a base to it, I end up with that lone pair of electrons and a negative charge in an sp orbital. And remember, sp orbitals are 50% s character, 50% p character. Remember, s's are spheres, and electrons in an s orbital are closer to the nucleus and more stable. So electrons in an sp hybridized orbital are closer to the nucleus and more stable than electrons in an orbital that's only 1/3 s character or 1/4 s character. So because that carbon is sp hybridized, it can stabilize that lone pair that we gain when we lose the proton. So alkynes are weakly acidic. Once we do that, we actually end up with something that's very nucleophilic. So this is very nucleophilic. Remember, nucleophiles are our electron sources. They're electron rich. So not only does this have 4 pi electrons, right? It also has a lone pair. So it's very, not nucleophile, nucleophilic. And it's called an acetylide ion. So it's a good nucleophile. So what we're going to do is we're going to do an acid-base reaction, end up deprotonating a terminal alkyne, and then I'm going to end up with a good nucleophile. That good nucleophile then can react in SN2 mechanisms. We should add, I didn't have that here, but we should add terminal, right? If it's not on the end, I don't have a proton bonded to it, so I can't lose a proton. So terminal alkynes are weakly acidic. Internal ones, I don't have a hydrogen to lose. I'm not going to pop off carbons. So terminal alkynes, weakly acidic. So I'm just going to rewrite that reaction here. I am going to show that hydrogen again. Usually when I do skeletal structures, I don't, but we're going to do the mechanism. I'm going to add a strong base. We're going to end up just doing an acid-base reaction. I'm going to end up with this, which is my conjugate base, and then I would also have my conjugate acid. My strong base, generally it's going to be H- or NH2-. You could use hydroxide. Hydroxide isn't as strong as these two, so these are going to be more common. And then again, do watch out. I'm generally going to have a cation with it, so sodium hydride, that sort of thing. We are going to do the mechanism real quick. It's just an acid-base step. So I do need to draw that bond out because we're going to need to show those electrons going onto that carbon. And then we'll use hydride ions. Seems to be my favorite these days. We're going to grab onto the proton. Those electrons go onto carbon. And then I end up with my acetylide ion. Negative charge on there. Other products, I do have H2, right? Hydrogen grabbed a hydrogen, so I have H2. And then I probably had sodium hydride, could be a different cation, but then I would have sodium floating around, probably hanging out next to acetylide because they have opposite charges. So just a straight deprotonation step. Once I make that, we can then undergo SN2 reactions. And I'm going to show two of those. So these are going to be substitution. This was just acid base if you want a title. You could say it's a deprotonation step. We use that term quite a bit in this class already. So we're going to undergo a couple substitution reactions. And our first one, we're just going to react it with an alkyl halide. So I have my acetylide ion, which you do have to prepare first. So I would probably start with the alkene. I would give you a strong base in one step, and then in a second step, I would give you the alkyl halide. And we can do some examples like that in a minute. And then I'm just going to use Rx. And then we're going to end up bonding that R group from the alkyl halide to my alkyne. It's going to be an SN2 mechanism. It's going to be best because it's SN2 with unhindered alkyl halides, so best with primary alkyl halides and then also methyl halides. So just one carbon bonded to that halogen. Are going to do our mechanism. And let's actually go through the whole thing. So kind of, I'm going to restart with just the reaction so you could see how I would give it to you. So let's have my terminal alkyne. And then in one step, use NaNH2. And then in a second step, we'll have this primary alkyl halide. So going through the entire mechanism, the first thing we're going to do is deprotonate that alkene. So I do need to draw out that hydrogen because I need to be able to show those bonds between the carbon and the hydrogen going onto carbon. Sodium I don't care about. I do have NH2-, right, and Na+, but again, group 1A cation is going to be inert. So we're going to grab that proton. Those electrons are going to go onto that carbon. And I'm going to end up with my good nucleophile. And then ammonia, NH3, as my conjugate acid if you wanted it. I'm then going to draw my alkyl halide in here. All of the normal SN2 rules apply. I am going to go through a backside attack. If we were to draw the transition state, right, we want to make sure that the bond that we're forming between the acetylide ion and that partial positive carbon is 180 degrees, right, from the bond that we're breaking between that partial positive carbon and bromine. I'm not going to show the transition state, but if we did, we'd want to make sure we had that stereochemistry correct. And then just be really careful to not lose carbons. It's super easy to do that. I do it a lot, even though I've been doing this for a really long time. So those 3 carbons are going to be these 3 carbons. And then that's going to be bonded to, I have 1 carbon here, 2, 3, 4. So I need to make sure when I do this, I have 4 carbons on there. And I always have to number these for some reason. So this is going to be 1, 2, 3, 4. So that's going to be the product that I get. So my carbon chain grew. This is the only reaction we've had in the entire semester where I'm taking the number of carbons in my reactant and I'm increasing it. So our carbon chain is longer, right? I started out in my reactant with 1, 2, 3 carbons total. My product, 1, 2, 3, 4, 5, 6, 7 carbons total. So my carbon chain has gotten longer. The second substitution that we're going to look at, we're just going to do 2, is I'm going to add it to an epoxide. So when we were doing our epoxide reactions, remember they were all ring openings. And we had 2 different methods, one where we added a nucleophile and then water in a second step, and then another one where we added acid. This is a nucleophile, so that's the version I'm going to use. So I'm going to put my epoxide here. I am going to make it unsymmetrical, and then I'm going to have water. And I'm going to end up, let me just draw the product here. And then that, the nucleophile, remember when we're doing this one, is going to attack the least substituted carbon. So I do have that methyl group on this carbon. Just be careful with stereochemistry too. I want this bond here to be anti to that bond. So I probably should have drawn this so it's a little bit more straight out. I know that stereochemistry looks kind of weird, but I just want to make sure that I'm showing that those are anti to each other, not that methyl group. So my notes that go with this, it is an SN2 mechanism, right? My acetylide ion, my nucleophile, attacks the least substituted carbon. It does go through the backside attack again, so my hydroxyl group and the vinyl group, right, my acetylide ion, once it's attached, is now a vinyl group, are going to be anti. So my hydroxyl group and the vinyl group are anti to each other. So all the rules that we had before when we were adding a nucleophile to an epoxide still apply. So let's go through our mechanism. And then I'm going to start with just the alkyne again, unprotonated. Sorry, not unprotonated, unprotonated, right? Still having that proton. And then I actually have to add a number to this. I just want to give you an example. So I'm going to use number 1, number 2, and then number 3, water, right? Before I can do these things, oops, didn't want to erase. Before I can do these, I have to deprotonate it first. So I'm going to deprotonate it, and then I bumps down my epoxide and water to my second and third step, because we have to do something before those. And I wanted to make that unsubstituted. So mechanism, I'm going to do that deprotonation acid-base step first. I have Na plus and H minus. It's the H minus, that's the base, right? My hydride ions. So it's going to grab onto the proton, and then the electrons between that proton and my carbon go onto carbon. Please don't forget that arrow. And then that gives me this anion. I'm going to throw my epoxide in here. We are going to attack the least hindered carbon, so that's going to be this one. Also remember, this was the one reaction that we had in chapter 9 where I didn't actually need to protonate my leaving group first or make it better in some way, right? If we were using PBr3, we weren't actually protonating it, but we were making the leaving group better. In this one, I don't have to. My nucleophile can just attack, and then that's where water is going to come in step 3. We're going to protonate it then. So I'm going to draw my product down here just so I have more room. So I'm going to draw the orientation. I'm going to keep this bond straight. So that's going to be this bond I just drew. I'm going to have this guy here, and then I'm going to have that hydroxyl. I guess it's not hydroxyl yet, my O- up, and then this is here. So those two are going to be opposite of each other. There's also a hydrogen on this carbon. We could do just like we did before. I could wedge it or dash it. Since I didn't give you stereochemistry on that methyl group, it doesn't matter if it's wedged or dashed. If I gave you stereochemistry initially, then you would want to make sure you keep that, because that carbon's not affected by the reaction. Now I can throw my water in, and we're going to, one of the lone pairs on that oxygen, right? There's 3 lone pairs there. It's going to grab onto the proton, and then don't forget, we have to break that bond, right? If we're going to grab a hydrogen that's already bonded to something, we then need to break the bond to what it was originally bonded to. So, hydroxyl group, my methyl group. This stereochemistry is more how I was drawing it before, so it probably looks a little bit better, though that alkene is pretty screwy. It probably looks a little better than how I drew it up here. It's just kind of tilted sideways relative to this one. Just again, be careful not to lose carbons, right? Here I have 1, 2, 3 carbons. So 1, 2, 3 carbons. And then 1, 2, 3 carbons, 1, 2, 3 carbons. So please just double check that you're not losing or gaining any carbon-based groups.